CLion, a cross-platform IDE for C and C++. Download now.
So if any of you have ever been to one of my talks before, you know that I'm very formal. And I ask everyone to hold their questions until the end. No, okay. So hopefully you intended to come to this talk, Consteval, all the things, question mark. And yeah, there we go, sorry. Making sure my clicker's doing what it should do. That's my normal title slide. My name is Jason Turner. I have a YouTube channel, yes, as Matt said. Be sure to like and subscribe. But if you don't know this, yes, I do have a YouTube channel. I've got 118,000 subscribers. That is out of date. I've been doing this for 480 weeks straight now. I realize, actually, once you include CVPcast, which is a podcast I used to co-host, I've been producing content for over 500 weeks straight, which is insane. But anyhow, I am an author. If you haven't checked out my books, feel free to check out my books. That's a that's a QR code for the YouTube channel. Those are links for my books if you're interested in those things. Also a developer, and if you're curious, I attempt to make the projects that are on my GitHub things that follow my own best practices. Of course, nobody's perfect at this, but I try. And I have been a Microsoft MVP for 10 years. I have my little 10-year disk on my crystal thing that they give. It's something. It's in the basement because I don't... To be fair, it's right next to my YouTube Silver Play button on the floor because I just don't display the things. Anyhow, I do training. That is what I do. I have to do these intro things. If you're interested in training, if you like my style, have me to your company. It will be a good time. Who was in my class? Was anyone who was in my class this week here? Yes. Hopefully it was good. And you can have, you can talk to one of them who had their hands raised, although Matt's cheating here because you were there, yes, but kind of as a guest speaker almost. I have actually been to Matt's company for training as well, many years ago, as a trainer, that is. And I'm happy to travel places. As you can tell, you might not notice I do have an American accent, but I have been to all of these countries for work. And if you missed my workshop on Monday at ACCU, I am hoping to give a similar C++ best practices workshop at C++ on C and at CVPCon and NDC Tech Town. So those are all accessible for, well, two of those are definitely very accessible for you here. My talks, avoid sitting in the back. Interrupt me and ask questions and yell out things. Don't hold your questions to the end. This is approximately what my training looks like. Just so you know, very interactive is my goal, less lecture is my goal. All right, oh, hello. I want to make a comment about Rainer Grimm. Who knows Rainer or has seen his talks or whatever? I don't know if you're aware, but Rainer, a lot of the room, just for the record, raised their hands. Rainer is a prolific speaker for many years now, published 9 C++ books. He was diagnosed with ALS and made this public October 29th of 2023. The last time I saw Rainer personally was in September of 2023 at NDC Tech Town. Let's see. So just so you know, ALS, it's also known as Lou Gehrig's disease, is a progressive nerve condition. It's different for every person, progresses in a different way for every person. Rainer went from an active lifestyle to needing wheelchair and breathing apparatus in about a 9-month time frame. So if you haven't been to his blog to read what's going on with him, he is updating it semi-regularly and talking about his ALS journey. I just want to say there's no cure, funding is lacking. If you have any interest in giving to ALS research or ALS therapy research, go check that out, please. Also, my wife and I are doing a walk across the Netherlands, May-June timeframe, and I'm going to do a €1 per kilometer walked, per kilometer logged on my watch, donation to an ALS group, and I'm going to invite other people to join me in on this too. I'll set up a Google Sheets or something so people who are interested. Okay, now on to the C++ stuff. C++11 added Constexpr. In 2017, Ben Dean and I did this talk called Constexpr All the Things. Have you seen this talk? I think it's fair to say it was influential. I don't normally like to say I was very influential here, but there's a lot of papers that were submitted to the committee that ended up referencing this talk. 2017, I also did this talk called Practical Constexpr, and then Applied Best Practices. In 2018, I accidentally made a Constexpr ARM emulator. I followed my own best practices, and my best practices say apply Constexpr everywhere you can. I ended up with an ARM emulator that can execute ARM code at compile time. It's just what happened. C++20 added Consteval, the point of this talk. In 2021, I gave a talk called Your New Mental Model for Constexpr. Oh man, that talk was good. It was so good, but it was in 2021. That means there were like 20 people in the room, and it was like because COVID, I wanted more people in the room for that one. Power of compile time resources in 2022, that was at, where was that? C++ North. Understanding the Constexpr two-step. I gave that one last year at C++ on C. And then how to use Constexpr in C++ 23. That was at NDC Tech Town. Has anyone seen that talk? No? All right, well, you should watch it. But the point is that by the time we hit C++ 23, generally speaking, how does one apply Constexpr to their code in C++ 23? No, liberally, yes, liberally. But more to the point, like, what is the mechanics behind it? You generally speaking, you just add the Constexpr keyword, right? That's basically all you have to do. And then in 2024, I gave this talk called The Runtime Cost of Using Constexpr. This, I am going to reference back to this talk relatively regularly in the talk today, because we think of Constexpr as being zero runtime cost, but that's not 100% fair. There are relocations that have to happen. So if you have something like a Constexpr table of function pointers, that is not just a mem copy or something at runtime, the loader, the operating system has to relocate where all those function pointers actually point to. Or if you have a Constexpr table of Constexpr string views, those are again pointers, relocations come into play. There is not truly zero cost here. It is possible to measure it, but it is a very low cost. And then here we are, Consteval all the things. That's, yeah. Is this compile time? Is this compile time? So I'm asking, is the value required to be computed at compile time? This is a tricky question. We're going to say, O0, optimization's disabled. We're not asking, will the optimizer sometimes choose to do this at compile time? The as-if rule, questions about observability of our code mean we can argue about these things. We're not going to do that today. The way the wording in the standard goes is basically like this function must be executed before any user code is executed. Practically speaking, these things are computed at compile time, okay? That's what we're talking about. All right, so is this call to make value done at compile time? No, we're not talking about the optimizer. You just broke rule 1. We're not talking about the optimizer. Is the compiler somehow forced to or required to say that this thing is evaluated at compile time? No. Okay. Is it now? Okay, for the remote people, we got a strong yes and then a bunch of no's. Several people said no. Why did you say no? I want to hear the arguments. If you go back to, yes, so the comment was it needs to be static Constexpr. And if you go back to some of my old videos where I talk about that, I will take blame for this. This is where I'm saying, yes, we can argue about the observability and such. I have done nothing to actually require a constant expression after this point. And in fact, with this specific example, can I reason about whether or not that value was computed at compile time? No, not really. I could dump the disassembly of a debug build and see if it sets up a value on the, oh, I mean, we could do that right now. No, that's 03. Yeah, it's not used as part of the problem, right? All right, let's put this at 0, and we can see that the compiler did, in fact, just pre-compute 10 and put that on the stack at 0. So that's the level that we're going to talk about. I did force constant evaluation of this function by assigning a Constexpr variable from a Constexpr function. So yeah, I need to, well, should redo some of those discussions. In the latest versions of my best practices book, I say, in this example, let's just assume this thing's computed at compile time. I have adjusted my wording on this. All right. Is this done at compile time? Notice I changed the call again. What's that? Possibly, okay. Not required. Just so you know, what depends on how I use it, okay? So the comment was if I put it into an array, then it would be. If I put it into a string, then no. Okay, or something like that. That was the comment. Just for the record, Claude got this wrong until I corrected it, and then it said, oh, you're right, you're right. Yeah, so Mateusz is like, so the standard actually does have this in the set of this is a core constant expression in the exact same wording that it has this version. I am initializing a constant integral with the result of a constant expression. So value is itself a core constant expression in this case. We can reason that our compiler, it is going to execute this thing at compile time. It is going to execute make value at compile time. And we can reason about that it would do this. What am I trying to say? I don't know. Does anybody know what's happening here? Right? So even at 0, the compiler's treating this as a constant expression. If I delete, yes, if I delete Constexpr now, then it's no longer going to do this at compile time. And we can see it actually. Oh, I don't know if you're familiar with this tool. Hey, to be fair, Matt, this is the first time you've been in one of my talks in a really long time. So we may as well at least appreciate Matt's effort on the compiler explorator here and the rest of I thank other members of your team every time they're in one of my talks, just for the record. Is anyone else who's a compiler explorer developer here right now? I don't think so. Yeah, okay. Yeah. So yeah, I removed Constexpr there, and this is a debug build, and this isn't going to depend on, I'm going to move it to Clang, and I'm going to, let's see. Constexpr. So yeah, it's the compiler's doing this thing at compile time. Little corner of the language. I did an episode on this called Stupid Constexpr Tricks. Talks about these things. All right. Is make value computed at compile time? What changed? Oh, sorry. Yeah. So I went from 2 and 4 hard-coded in there to passing the parameters A and B. No. No, A and B are not constant expressions. Okay. Is this done at compile time? Matt already cheated. So we've already looked at this, but go ahead and remind me. Is this computed at compile time? No, because it's no longer a Constexpr function. The compiler's not going to do that here. All right. And we can actually watch these things trace down. All right. Is this computed at compile time? Who says yes, this is going to be computed at compile time? Who says no, it's not going to be? Oh, we've only got 2 people raising their hands. Why? Why are you saying no?
It might be due to the floating point expression.
But I probably shouldn't stand right in front of the speaker. That could cause a problem. And yes, I do try to make sure the cameraman stays awake in my sessions. You said because floating point, but I am initializing a constant expression with a constant expression. Like I'm gonna reason say this thing is computed at compile time, and let's just go ahead and put it in the verify our things here. Yes, okay. So yeah, that there's no math happening at runtime here. All right, just making sure. You all are making me question my slides right now. Loading point, but it's just Constexpr. Okay, is this computed at compile time? It's not the same slide. Oh, they are doubles. I should have had W conversion turned on. Yeah. Are you being serious, or are you just? Oh, okay. Yeah, no, it'll still allow that at compile time as long as all of my slides compile. I mean, I literally compile all the slides except for the ones that I have explicit comments in them that you can't see, they get stripped out, that say don't try to compile these slides. So yeah, this compiles. But okay, is value computed at compile time here? We have to do a show of hands. Who says yes, it is? Who says no, it's not? Okay, the answer is no. I'm going to go back to this one. Do you remember the wording that I said here? Oh, sorry, that one. They have to be integrals. It must be a constant integral initialized with a constant expression to fall under that special case of core constant expression. This is why I'm not on the standards committee. Plausible deniability. I didn't do it. Okay, so no, this is not required to be computed at compile time. This is not an integral that I am initializing. All right. Ooh. Is this one computed at compile time? There's murmurs of no's across the room. Okay, who thinks that this is done at compile time? It's fine. Go ahead, raise your hands. It's fine. It's fine. You pay attention to other C++ educators in the room and whether or not their hands are raised. This is constant initialization, which will be, just so you know, the rules around constant initialization hung my meetup up for 30 minutes when I gave this talk the last time, so we'll see what you do. Okay, so constant initialization. If a static is initialized with a constant expression, then that static is constant initialized. And this is where the wording basically says it has to be initialized before any user code is executed. So hypothetically, it could actually do this initialization somewhere else in the linker. I don't know, whatever. But no, I think the wording is stronger. You can't, it's not global constructor. Or like if it was gonna be like a global constructor, it has to be before we get to any user code. All right, yeah, so that's constant initialization, static initialization rules. Okay. Is this value now computed at compile time? No, because it's not a constant expression on the right-hand side. All right. Oh, hello. Oh, my thingy is, yeah, all right. All right, so just so you know, constinit by itself does not change the meaning of code. It verifies our assumption that constant initialization is occurring. Constant initialization happens whenever a static object is initialized with a constant. There's one more bullet point here, just so you know, Matt. Happens every time a every time static object is initialized with a constant expression. Constant initialization means that the object is initialized before any user code is executed. Oh, sorry, there's another bullet point, I forgot about it. Like override, it doesn't change the meaning of the code. If I had code that compiled and did what I wanted with the override keyword there, and I remove the override keyword, my code still does exactly the same thing, okay? If I had code that compiled and did what I wanted with the constinit keyword there, and I remove the constinit keyword, my code still does exactly the same thing. Does that make sense? Who's used to using override? I was gonna say, if you don't raise your hands, you better hire me for training at your company. All right, so constinit, static, auto, blah, blah, blah. Is this thing initialized at compile time? Yes, it's right there, right? All right. Is this initialized at compile? What did I change? Oh, I took Constexpr. Okay. Is this initialized at compile time? Does it compile? Constinit enforces my assumption. If I put constinit there, I'm saying I want to constant initialize this thing. Constinit must be static, and it must be initialized with a constant expression. So this code does not compile. All right. What was my point? Right. Consteval. We haven't even mentioned Consteval. Consteval functions are known as immediate functions. They must be evaluated at compile time. They must be evaluated in a Constexpr compile time context. This is a Consteval function, and is value initialized at compile time? Yeah. Its value is computed at compile time. Yeah, it's Constexpr, Consteval function. I have just made, oh no, wait, sorry, that one. Everyone said yes, even me. I keep getting myself confused on this one. This can't compile. You can't initialize a Constexpr variable with a function parameters. No, wait, the Consteval function doesn't exist at runtime, but that's not the point. The point is A and B aren't constant expressions. So this can't compile. Whether or not there's a function is irrelevant. The point is A and B. The point is A and B. All right. All right. What am I changing here? Okay. Oh, I made func itself Consteval. Can this code compile? No. No matter how much we would like, parameters are never constant expressions. Unless someone on the committee changes this at some point. It is correct. Let's double check. Doesn't compile. I was right. No, so make value, so to initialize this constant expression on the left-hand side, I must pass constant expressions. Parameters are just never constant expressions. Oh, sorry.
The transient property is parent function is Consteval, and then sort of where you pass the constants in there and sort of a transition all the way down.
So the problem is that I'm trying to initialize this Constexpr variable here on line 5. Oh, repeat the question, sorry. The transient property of being able to call constant expressions down, the function calls, basically, yes. So if I was trying to initialize a constant expression value with a function that I correctly pass constant expressions into it or whatever, and then it computes some intermediate values and it calls another Constexpr function and it calls another, yes, that's fine. The problem is that I'm trying to initialize this object right here, value Constexpr, with these parameters, and those parameters can never be treated as constant expressions. But I could return that out of the scope and treat the result of this thing as a constant expression. Yes. Okay, hold on. I saw the eyes that made me say, wait, what? So this okay. Have you fixed this bug yet, Matt? No. Oh, it doesn't matter. I haven't updated my compiler explorer anyhow, so I was gonna. Okay, so it's that Constexpr on line 5 is ultimately my problem. If I delete that, then yes, I can do this. I can take constant expressions, pass them into some other function. I'm just gonna go ahead and prove that I can then like compute intermediate values and whatever, and I can return the thing. And now the warning that I'm getting is v is unused on line 11. Is that what you were asking? Yeah, this is totally valid. But if I try to, what's that?
Why can it be Constexpr? Because surely it just folds into it.
Join the standards committee. The question was, why can't the thing on line 5 be Constexpr? Because surely, and you're like, it's a const eval function. Its parameters are required to be constant expressions. Sorry, I didn't do it. What's that? Yes, I'm correct. But it's terrible, yeah. I know there's been discussions about trying to make the thing that we just discussed with Constexpr there valid code, but they haven't. Oh, right. So the comment was that there's a proposal to put a Constexpr on the argument. So you can say this is an argument. Okay, so if we actually wanted, how much time do I have? Unknowable. Oh, Matt, you said I have like as much time as I want, right? That's right. You can take all of my time. Very good, okay. This is currently how we spell Constexpr parameters. What did I break? Yes. Oh, B is still not a okay, yeah. B is also still not a constant expression. It's exactly what we just spent the last 5 minutes talking about. All right, now why is it failing? Too few arguments. Because I'm still passing in a parameter. No. Oh, goodness gracious. There we go. Is it going to compile now? Okay. So yes, that is how you, if you want what you would think of as a Constexpr parameter, non-type template parameters is the way to do that. The other way, actually for real, how much longer do I have? I still have a full hour, right? All right. The other way to do this, nope. This works for captureless lambdas. So you can pass a captureless lambda in and use it to generate a constant expression, or a function pointer. There's special wording that specifically allows this kind of thing. It's one of Ben Dean's favorite things. I've also used it in a few talks as well. It's a way to do things. Yeah, go ahead, take pictures if you would like. Let's see, the understanding the Constexpr two-step talk that I gave at C++ on C last year goes into more detail on this, and the last couple of talks that Ben Dean has given also talk about this kind of thing. All right. All right. Parameters are never today able to be constant. You're going to love the next slide. Trust me. But you can have arguments that produce constant expressions. But that's not the topic for today. I guess we did it anyhow. All right. Okay. So that compiles. All right. Okay. This does not compile because, again, A and B are not constant expressions. It does now compile again because A and B are constant expressions. So calling a consteval function requires constant expressions. This thing result is computed at compile time because this immediate function, as Mateusz pointed out, it's a function that it doesn't exist, basically. You're never going to see the body of this function emitted into your binary. It doesn't exist. Wait, you're saying if I make everything consteval, I have no ABI issues? Yeah. That sounds perfect to me. All right, so constant evaluation and undefined behavior. This is, there's lots of wording around this. What is a core constant expression? The expression E is a core constant expression unless the evaluation of E following the rules of the abstract machine would evaluate one of the following. So it's basically presumed to be a core constant expression unless. And one of the unlesses is an operation that would have undefined or erroneous behavior as specified in intro through CPP. There's a couple of random takeaways here. First of all, erroneous behavior. Who is familiar with erroneous behavior? Very few people. That was wording added in C++ 23. This is where like the read of an uninitialized value is now no longer undefined behavior. It is erroneous behavior, and it's trying to make our compiler slightly more predictable. Would that be a fair way of saying that? Something. It still doesn't say that a read, you're not going to get a specified value when you read an uninitialized object. You just don't have undefined behavior anymore. And the rules for undefined behavior basically say if you have undefined behavior in your program, the compiler is literally allowed to do anything it wants to do. It can hack your Tesla, it can open your garage door, it can format your hard drive, whatever. The other little interesting thing here is, well, it's not specified here. The standard library is specifically exempted from these rules. There's another chunk that exempts the standard library, as pointed out to me recently. Okay, so Constexpr and undefined behavior. I have this Constexpr function. It's called func. That's how you know it's a function. That is doing something that it should not do. Do you see that, I assume? Now, the compiler is basically required to allow line 7 to compile, and it is not allowed to let line 8 compile. So if you didn't know this, you can apply consteval to lambdas. So I have an immediately invoked consteval lambda. Why did I do it like this? What's that? You know, save space on the slide was the comment. That's not exactly what I was going for. Force it to compile time. Why didn't I just assign the result to a constant expression? There isn't a result. It's void. Right. Okay. Just making sure we're on the same page here. This is like, I mean, it's not the only way, but it's a really fun way of forcing a void function to be evaluated at compile time. Throw it inside a consteval lambda. Excuse me? It's very clear. Yeah. So I think it's clear. And also the other thing that there's two other things you might not know here. First of all, lambdas can be consteval, yes. If you know every single thing that there is to know about lambdas, then I would argue you probably understand about 90% of the C++ standard. Because lambdas, every time the standard is updated, lambdas are updated to follow along with the standard. And, oh, also rule change in C++ 20, that I'm not required to have the empty parameter list, even though I've specified the consteval right there. Before C++ 20, I still had to put, is it 20 or 23? 23, sorry. Then I would have still been required to have the empty parens there because I added the consteval. Anyhow, I'm forcing the compile time. This won't compile. Okay. Erroneous uninitialized read. Line 7 compiles, line 8's not allowed to compile. I did just double check all of these, just so you know. Depends on compiler version. C++ version, no. Oh, yes, but yes, you're right. In 17, line 2 wouldn't compile, but in 17, line 8 wouldn't compile anyhow. Consteval doesn't exist, so yeah. Yes, in 17, you were not allowed to have an uninitialized variable in a Constexpr context. End of story. You had to initialize everything. After C++ 17, you have to initialize it. You have to give it a value before you do something with it. You still aren't allowed to do an uninitialized read in Constexpr. All right. Okay. Signed integer overflow. My meetup members hated the fact that I did this as like just a 0 with 31 ones after it. I just thought it was the more readable way. I've overflowed into the top bit. Let's signed integer overflow. It's very clear. This won't compile. You're not allowed to do signed integer overflow. That is explicitly undefined behavior in the standard. Yeah. Yes, I said I double-checked all the slides. It does, okay. The comment was it depends on the architecture. How many, okay, all right. We're gonna play this game. What's the size of an int on your architecture? Yeah, typically 4 bytes, 32 bits. We say typically on every platform that is at least a 16-bit platform, I believe they chose 32-bit for the integers. Maybe it's everything 32-bit and later. No one changed. When we went to 64-bit, none of the compilers changed to make int 64-bit. And can anyone name platforms where int is not 32-bit? Pick, yes. Another one? 6502. Hey, don't bother laughing. There is an LLVM MOS fork that's maintained, and you're going to get 16-bit int there. Anyone know another one? Maybe the SH2. I don't know about that one. I can think of 2 more. The MSP 430, because it's also an 8-bit processor, right? Or it's a 16-bit processor. It's 16-bit? Or is that... There's one more that I know for sure uses 16-bit int. What? And Windows 16-bit, yeah. That's old. I mean like a currently maintained CPU. I don't know, this is just a fun game for me, so we can move on. But AVR, yeah, AVR is an 8-bit architecture. Okay, so yes, it does depend on platform, but if you're using any of the platforms that are supported for execution on Compiler Explorer, currently, Execution? You do support 6502 execution. But you don't have a 6502 backend right now, do you, for C++?
Yeah.
You do?
We have one of the other VMOS ones.
Oh, you do?
C.
In C. Then you,
All right, okay.
all right. Okay, so this uninitialized return value, this also can't, so in returning this I, that's a read of an uninitialized value. I can't do that either. All right. Write past the end of an array. Can't do this. This won't compile in a consteval context. If you can make your code Constexpr, just for the record, you can catch all kinds of interesting undefined behavior if you can then also test that code in a Constexpr way. I was asked to not put my back to the camera too much, but well, you know, here we are. This will become relevant later in this talk. Do you see? I have comments, but do you see why this doesn't compile? This is a little bit tricksy. The storage doesn't go into runtime, but okay, what is a very simple change I could make to this code so that it does compile? No, static isn't gonna let it, what's that? Just the return the string literal. So I've done this weird syntax of where I've actually said, make a local character array on the stack. And that's the problem. This thing's gonna automatically decay to a pointer. And this is, I mean, I actually literally recorded an episode that said, the one feature I would remove some C++, and it's the array to pointer decay, because it's so dangerous. That's going to decay to a pointer. That's going to implicitly convert to string view. The string view is now going to have a pointer to data that's no longer on the stack, or that's been popped from the stack. And then line 10 becomes undefined behavior. That code can't compile. Well, I guess it's not. When does the undefined behavior actually happen there? You're allowed to have a pointer to invalid memory. You're not allowed to have a reference to invalid memory. Well, at some point it's detected. All right. What's the actual error? Call to consteval, blah, 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 not a constant expression. Not a constant, okay, that's not very much information, GCC. Address of stack memory associated with local variable returned. That's a much better error. Pointer to sub-object of data is not a constant expression. All right. I should speed up. Constexpr versus consteval. For function declarations, a Constexpr function is a function that you may invoke at compile time. Consteval function is a function that is invoked at compile time. For variable declarations, Constexpr is an object, now becomes a constant expression itself. It can be used wherever a constant expression is required. For consteval, that's the syntax error. There's no such thing as a const of the eval object. What's that? That's everything. Oh, that's a pity, sorry. I don't, but what would it mean that Constexpr doesn't already imply? So you would want a consteval object that is a constant expression, but you could modify it at compile time. And then it doesn't exist at runtime. I haven't thought about that. We might have to, all right. If Constexpr versus if consteval. These things are basically two completely different things. I feel like I have to cover it as long as we're talking about consteval, though. If Constexpr forces this check to happen at compile time, and then it effectively compiles the block that succeeded, right? So this is one of my go-to examples here. If Constexpr, the param is floating point, then I am, is not floating point, then I'm gonna do integer modulus to calculate the remainder. If the parameter is not floating point, then I'm just going to return 0. Because I'm gonna say, I don't know how to do floating point remainder in this programming language, although years after I first came up with this example, I learned that floating point remainder is a thing. Oh well. But it's still like, whatever. We can't do the modulus operator on floating point numbers in C or C++. So on line 13, I get 1 returned because 1 is the remainder of dividing 3 by 2. And on line 14, I say floating point remainder doesn't exist. I'm giving you 0 because I can do it's 0.5, whatever. Like there is no remainder. That's the argument I made here. If Consteval asks the question, are we in a compile time context? So if I am in a compile time context, I'm going to do integer modulus. If I'm not, I'm just going to return 0. I'm just making, this is really slideware, right? So note, I'm abusing the rules here, but also proving a point from the intro slides. This thing, this thing, const auto val 1. Now, I am initializing a constant integral with a constant expression. Therefore, it's going to compile the consteval block. To the reader of your code, this is not obvious that this thing now counts as constant evaluation. But we know the rules because we've been here for the last 45 minutes. But this thing is not going to be constant evaluation because these parameters are not constant expressions. So I'm going to get 0 returned. Make sense? All right. This is the bonus point slide. What value is val2 going to be now? Is P1 a constant expression? Is it a constant integral that has been initialized with a constant expression? Yes, it is. Yes. And literals are constant expressions. Yes. So P1 is a constant expression. Is P2 constant expression? Am I passing constant expressions to a function that's Constexpr that's initializing a constant expression, a constant integral thing? Am I going to get constant evaluation? What value am I going to get returned from main? That's a good question. Yes, this is super not obvious, but it's fun. Okay. What value now? 0. So this, like, can we argue about whether or not these things are constant expressions? I love these examples because they force the rules, right? It does cascade. Yes, the compiler is treating these things as constant expressions. And I just want to say for the record, if your goal was to create a constant expression here, please type Constexpr. All right, make it clear to the reader of your code. Don't rely on these rules. All right. So these things still aren't even relevant. Oh, we haven't even gotten to the point of this yet. Whew. We're good. All right, what can be consteval? Free functions, constructors, member functions, conversion operators. That's the bit that I didn't realize until like a week after I gave this talk the first time. Many of the special member functions, destructors were approved for C++ 26. Consteval destructors is for my understanding, because I got a correction from someone. And user-defined literals, which I must blame Matt for actually calling to my attention. Consteval free functions. We've covered these things. They are 0 asterisk runtime cost. That asterisk referring back to the understanding the runtime cost of constant expressions, okay? So if these things have relocations, that's not truly 0 runtime cost. It's small, but just so you know, there is code emitted for this. And no asterisk undefined behavior during execution. Why the asterisk on the no undefined behavior? Quality of implementation. Compilers are not 100% good at catching the undefined behavior during constant evaluation. Cons. Requires constant expressions for the arguments, as we saw, and we can't like fuzz test these things. And in general, fuzzing them and debugging them is hard. Apparently, you talked about this at a talk you gave this week, a bit, and I wasn't at that talk. And you're getting ready to leave, so maybe someone else can fill me in if I missed something that you talked about. All right. Consteval constructors. This code is designed to be played with. I have my basic string view. This is the super cheap version of the standard library string view. Both string and string view are actually basic string view and basic string, and the thing that you think of as string and string view are type aliases for a basic string view of car, okay? So I've played this out here, basic string view. I have a constructor that takes a character pointer. I'm initializing the members. I am properly, correctly using the stud car traits, car type, length thingy here that counts the length for me. This is how string view works. It's how it's going to initialize this thing. All right. So if I need to put this is to be able to really talk about this, I'm going to put this in Clang. I'm going to take this down to O0. We're going to basically say, yes, look, it generates all of the code where it has to, call the count and counts the characters in the string and all the stuff. If I make the constructor Constexpr, this isn't going to change the O0 debug build. I said this thing is allowed to be called at compile time, but the thing that I'm initializing, sorry, it's off the screen. The thing that I'm initializing is not static. It's not a const integral. So it's not required by any definition to evaluate this thing at compile time. If, however, I do make this thing Constexpr, then I'm going to see that I'm going to get that call to that constructor removed at compile time, and it's just doing a bunch of stack manipulation stuff, basically. If I take away the Constexpr and get to discussing the point of this talk, where I make this consteval, then this is also going to force the construction of the string view-like thing to compile time. That means I can only create my string view with a character string literal, or a Constexpr static, whatever, Constexpr string, a character array. I could also construct it with that. But basically, what I have done here is I have said, I know, if that's consteval, I know at construction that that string view thing on line 21 is safe. What's the main problem with string view? Dangling. If I can make my constructor consteval, I know it's impossible to have a dangling string view. Compiler won't let me. That's neat. Is it useful? Yes? Useful, at least in some cases, though. How often are you creating a string view from, say, a standard string object? Yes, the standard string object, that's where the problem is. If I'm only creating this thing from character string literals, then I don't have the dangling problem anyhow. If I'm creating it from standard string, then I do potentially have this dangling problem. All right, so this thing, 0 runtime cost, no undefined behavior, like we just said, I cannot create a string view to a temporary. Requires constant expressions for the arguments. I still can't test this thing in the ways that we're used to testing it. So the question is, do I make that string view consteval? Who says yes, I love the idea. I'm going to make my own string view type, and the constructors are consteval. I like it too, but just for the remote people, there is only one person, not including me, raise their hand. Maybe I do, but I changed the name of the class. What if I say I have a basic safe string view now? This is a safe string view. I guarantee if you're using this string view, it's impossible for you to have a dangling reference here. What's that? Literal string view? Okay. What, we're gonna have to dig into this in later slides because I have a lot. Shoot, okay. All right, so maybe also we consider making some of the constructors Consteval. What if I said, okay, I have a Consteval constructor that when I'm passed a character array, which a string literal counts as, then I force it to Consteval, so it's impossible to create a string view to a local character array. I've at least made it slightly safer. I believe we could add that constructor overload specifically to the standard today without breaking anything and making some use cases safer, I think. If not safer, at least more performant. Now I know that the string view is going to be, well, if I create it with a string literal, I know it's not gonna have any runtime overhead. All right, Consteval members. This is fun. I have my basic string view, and I have now made the size member Consteval. Do you see the implications of this? I said all of the parameters must be constant expressions. How many parameters does size take? 1. An implicit this parameter. So your this pointer must be a constant expression or evaluated in a compile time context. Going back to the questions about, like the call chain, it must be constant expressions. Okay, so this code compiles because I'm calling sv.size on a constant expression. If I were to make a copy of this thing, like on line 21, this code doesn't compile anymore. SV, what's that? Unless I also make it a constant expression, yes. But I'm trying to make the point of when and where we can't call it. And yes, to bring this home, yes, if I call this whole thing in a Consteval context, then yeah, I can create this thing. Now notice SV here on line 19, it's not Constexpr, but I can still call .size on it because I am guaranteed to be in a constant evaluation context here. All right. It's the this that has to be Constexpr. We already said that. Okay. So requires constant expressions for the arguments, including this. If member data is accessed, that's a key one. Sorry, I skipped over this slide. So notice if I were to make the size member of array Consteval, that can always work. Because I'm not accessing member data, that thing's a compile time constant, that's fine. Okay, still can't test these things in a typical way. So which members would I default to making Constexpr? Consteval. Yes. Which members would you default to making Consteval? What? Destructor. Not yet. We have to get to destructor in a minute. So I would say members that don't rely on this, or could be static, or if using the member with a runtime value would somehow be an error in your code. If you want to say, I want to enforce correctness, this thing must be executed. This must be called a compile time thing. Consteval default constructors. This code goes several different directions. If I've got this data struct here and I've just equal defaulted the Consteval default constructor, I've explicitly defaulted the default constructor to make it Consteval. Now, what does that constructor actually have to do? It does something. It zeroes out those 256 bytes. So I can, what's that? 256 ints, not bytes, yes, sorry. So 1024 bytes probably. 512, unless if we're compiling on our 6502 or AVR architecture, yes. Yeah, All right. So there's a bunch of different ways that I could do this. You can make some initialization routine, make it Constexpr. You can make the default constructor Consteval. You can, let's see, how did I do that? Consteval static, so that's the initializer. I made it Consteval, and I'm initializing the member thing with the Consteval function. So I'm forcing this thing to be initialized at compile time no matter what. Or I could, do it like this, right? So this way, okay. Or I could use the member initializer list, and I could use that to initialize see, I made the default constructor Consteval. I'm initializing values with the Constexpr function. I came up with at least 4 different ways of doing this. They're all like at least moderately interesting here. But yes, so you can make your default constructor Consteval. And this question has come up whenever I've talked about this. And so people assume if I were to say have a vector of these things where the default constructor is Consteval, then surely I can't actually use that vector. And that's false. You can. You can push back into this vector of things with a default constructed thing or in place back, and the compiler just knows that it has to initialize, like that thing will happen at the work happens at compile time, but it's fine. It should be fine. Let's double check that it's fine. Yeah. Yeah, the big table right there. The big table. Woo! Yep. This one's actually initialized. Yeah. I started moving faster because of time. This one is actually initialized with iota just so that we can actually see it generate this table. And if I turn this down to 0, I'm still going to see the table. And because I'm requiring this thing to be initialized. And so now every time I do a push back, yeah, it's going to copy that.
That might be a personalization from like just doing it.
It might be a pessimization. That's not the question at the moment, though. Yeah. And Clang is doing this wrong. Clang is actually like doing the work to initialize this thing. It's not copying from that table. Yeah, compilers. Okay, all right, let's see what we can do. Okay, so the question is, so we can do that. Let's go back to our basic string view thing. Should I make my default constructor for my string view Consteval? Is there any harm to making it Consteval? Could it possibly you have harm? Bring back copy on write strings. But that doesn't matter for the default constructor case, right? All I'm saying is in the default constructor that I know that I'm going to initialize this pointer and the size t thing with zeros. I'm copying probably 16 zeros onto the stack or whatever. Now, we've been here for an hour. Is my time right? Do I still have 25 minutes, right? Okay. Would you make this default constructor Consteval, having reached this point? I would. I'm to the point, yes, I would. All right. So one of the things about Consteval functions is they don't exist. You cannot take a pointer to a Consteval function. I learned that while preparing this talk. You can inside constant evaluation, but outside constant evaluation, you can't. Not legal code. So is that a problem that I can't create a pointer to this default constructor? No, because there's no syntax to take a pointer to a constructor anyhow. All right. Cons, I don't see any cons to this for this kind of thing. So which default constructors do I consider making Consteval at this point? All of them? Everyone that can? I'm pretty much to that point. Binary size isn't, if you're initializing big data tables like we did in the slideware example, yeah. If I'm initializing this, might make binary size go down. Maybe. In an optimized build, I would expect that constructor to effectively be elided anyhow. In a debug build, yes, it's going to make the binary size go down. Doesn't matter. But let's just say hypothetically that this default constructor might have had undefined behavior in it. It did some work, but not enough work to generate a giant table. Making it consteval would force the compiler to catch that undefined behavior. All right. Consteval copy constructor. This one's fun. So, I'm using C++23 syntax right here on line 21. If you're not familiar with that, you can have an explicitly unnamed thing underscore. That's weird. We're not going to get into that right now. But line 20 works fine. I'm constructing this, my basic safe string view with this pointer to a character literal. It's consteval, everyone's happy. But on line 21, I can't make a copy of this thing at runtime, because the one parameter that that copy constructor needs, the thing to copy from, is not a constant expression. Now I can copy it. I made it Constexpr. Now, who was it who raised your hand and said, yeah, I like this basic safe string view thing with the consteval? There was someone over here that was like, the good times, right? Okay. It's an interesting world that I want you to at least think about when you leave this session and say, there is a source of truth here. I know that this thing was safely initialized, and therefore I'm only going to copy it if I know that it was a thing that was safely initialized. Ponder it. Whether or not it makes sense here is its own question. All right, so requires Constexpr object to be copied from. Which one do I default to making consteval? In this case, I would say when I can argue, like I just said, that there's somehow a source of truth. I know that that thing is valid. Therefore, I'm going to make the copy constructor consteval. All right. Consteval move constructor, copy assignment, and move assignment. These things are weird. If I say a consteval move constructor, you can't move from a const object anyhow. So if I'm going to require the thing being moved from const to be Constexpr, I can't move from a Constexpr thing. That doesn't make sense in that regard. So all three of these things are only usable in constant evaluation. This example down here, lines 21 through 26, all of this compiles, but this is the only place that these things are usable. Yeah?
So wouldn't it be a better idea to use if consteval inside?
Wouldn't it be better to use if consteval inside the copy constructor and such? I'm going to say no, because then if I'm actually providing bodies for these things, they're not trivially copy constructible. It's like becomes like a thing. And then I personally think if constevals should be used very sparingly, because you really don't want your code to have completely different behavior, compile time versus runtime. I can say the only use case for this is to force the object to only be usable at compile time.
No,
All right.
Hey, Jason.
Yes, sorry.
On that side, if
Y-
the
yes.
point is to be safe, why not implement the move as a copy?
Why not implement the move as a copy?
Because the move doesn't.
Well, no, but in this particular version, the move's going to be a copy with this anyhow, right? Because that's all trivial stuff. May as well. So for the video, why don't you may as well just make the move as a copy, make it legal. It still couldn't actually call this thing in a non-constant evaluated context because a const object is never going to bind to the R-value reference parameter of the move constructor, so I still can't call it outside of this context. But also, I'm just going to say, while I have everyone's ears, I do strongly encourage you to follow the rule of zero. Don't implement your own special member functions unless you have a very good reason to, and most of your very good reasons are wrong. All right, I definitely don't have time to go into that. So these things, like none, I don't know. If you want to force your type to only be usable in constant evaluation, maybe, okay. Consteval conversion operators, these are the slides that are completely untested, but we're coming back to our basic safe string view. Do you said I did on line 11? I should have highlighted it. Do you see it? That is a consteval conversion to underlying pointer type. What's that? Right, so string literal to pointer would happen automatically, but this is my string view type. So now my string view type is implicitly convertible to a string pointer, but only if the object was Constexpr. So normally, I despise implicit conversions, right? I don't know if you've heard me say this in any of my 400 YouTube videos where I've mentioned it. I hate implicit conversions, but I was asked by one of my meetup people, are there implicit conversions that you might tolerate in certain contexts? And I started to think, well, if I have a const eval implicit conversion to something, so for this thing to be callable, I know that my basic safe string view, its const eval constructor, must have been constructed with a null terminated string. Therefore, I know it is safe no matter what to convert this thing back to a string pointer, and it can never be dangling, and it's always going to be a null terminated string. Maybe I allow this to be const eval. Maybe. Yeah, so could I construct this with a Constexpr array of char that doesn't have a null terminator? No, that would fail to compile because I'm using the car traits length, and when that thing tried to calculate the length of the string at compile time, that would fail to compile because it would iterate off the end of the array. So it has to have been created with a null terminated string. What's that? It has to be null somewhere. Well, it has to be null somewhere. But it has to be in that contiguous array, otherwise it would fail to compile. That'd be at UB.
And you've taken away that template one that took the car.
Yeah, I took away the template one that took the explicit character array. All right, so, my whole point of my talks is to make you think. I think this is maybe is a valid use case for a const eval implicit conversion operator. All right. Forces, conversion, okay. All right. So which conversion operators would I default to making const eval? Conversions that might be problematic, or in some way I can say this guarantees the safety of this thing. All right. Const eval comparison in spaceship. Same restrictions as move and assignment. Can anyone think of a use case? I say these things should only be comparable if they're Constexpr objects. If it contains, yeah. Yeah, if they're invalid, there's no point in comparing them. We have to, but it's like tricky. I think finding a specific use case where I'd be like, well, yes, obviously you should have made your defaulted spaceship operator const eval here. I haven't been able to construct that in my head yet, but maybe if you have one. Constexpr destructors coming in C++26, like that. This code, I can't compile this code. No compiler supports this yet. What would be the goal of making my destructor const eval? There is a reason for this. RAII during constant evaluation, yes. But there's a temporary objects during construction. There's like a bigger picture thing here. If that thing is Constexpr, its lifetime must end during constant eval. Excuse me. If its destructor is Consteval, not Constexpr, it's Consteval, its lifetime must end during constant evaluation. It is impossible. Like, that code actually can't compile. It's impossible to use this thing outside of constant evaluation. Its lifetime has to end before. So it would be, there's people in my meetup that are like, yes, I want this. Then I'm like, I know that type will be fully evaluated at compile time. If you want to really force stuff to compile time. For some people, there are, yeah. You say, like, and basically it does come down to saying, like, this thing, yeah. So this can't compile, this would compile once this is added. It was added in 26. And it comes down 100% to saying, I want to guarantee that this object does not persist to runtime. Whatever your logic might be for that. All right. So which destructors do I default to making consteval? Only the things that I say, like, well, it's not possible yet to demonstrate. Only the things that I say, this thing must be used at compile time. I'm trying really hard to not actually butt into Matt's talk here. Consteval UDLs. This is where I have to actually very specifically thank Matt, because he first brought this up to me 4 years ago or something at this point. Like, as soon as Consteval was actually usable, Matt's like, I think UDL should be Consteval. And I'm like, what are you talking about? So what is a UDL? User-defined literal. User-defined literal. Are its parameters constant expressions? Yeah. They have to be. It's right in the name. Should I make my UDLs Consteval? Probably. All right, there's use cases where I can't. What use case can I not make my UDL? There's one in the standard, one very specific UDL in the standard. You cannot make Consteval. What's that? Locale? No, sure, yeah, yes. That's not what I was going for. Are there chrono ones that use locale? Is that what you just said? I don't think so. That's not what I'm going for. There's a more obvious, a more commonly used one. It's strings, the SUDL that returns a standard string. That can't be Consteval because it's going to force compile time evaluation of the string object that's being returned. Can't do that. You have to destruct that string object at compile time. That's meaningless. String view, absolutely. SV, that thing needs to be Consteval like yesterday. Someone should write a paper for that. All right, keep going. Matt, have you done that yet? You're the one who brought it up to me. All right, whew, I gotta keep going. So it requires compile time literals, but they are. The real problem is that the returned object must be allocated. Which ones do I default to making Consteval? All of them. If you're writing user-defined literal, make that thing Consteval if you can.
The real big thing about this is, the real big thing about this is that if you have to do any kind of parsing in the sort of UDL yourself, because sometimes you have like a string, you're parsing it, you can throw an exception and get a compile time error if you screw it up.
That sounds neat. Did you hear that? The people remotely didn't. If you have to do some sort of parsing inside, or parsing if I'm going to translate it to British, inside the inside your UDL, then you can like throw an exception or somehow have undefined behavior or something like that. You will get a compile time failure if that thing was invalid. So now you've just done a compile time evaluation of your user-defined literals like syntax or whatever as well. All right. Consteval lambdas. We already showed that. This is a handy way. I've got 10 minutes. This is a handy way of forcing work at compile time, basically. Bam, use Consteval lambdas. Which ones do I default to making consteval? Captureless, things that don't take arguments. Things that don't take arguments. Anytime I want to ensure initialization of an object at compile time, it's handy to wrap Constexpr functions and immediately invoked consteval lambdas to force them to compile time. It's a fun trick to keep up your sleeve. Should the consteval lambda also be static? I know it's 10 minutes. I just said that out loud. I know he's doing his job. Consteval free functions. There's more to discuss here. So should this thing be Constexpr, consteval, neither, both, what? And it can't be both. This is one of my go-to examples with students for consteval. It can be Constexpr. This is the kind of thing I'm going to default to making consteval. I'm sure most of you have written something like this, although product name is probably inserted by your build script along with like build SHA or something, right? Like these things exist often on our tools so that we can somehow print a nice pretty statement to the user. You're on version 1.01 R32 or whatever, you know. All right. Requires arguments to be constant expressions. Returned object must not allocate. So we're starting to see a pattern. Which ones do I default to making consteval? Functions that could be Constexpr but don't have parameters. If you have a free function that could be Constexpr, takes 0 parameters, you probably want to make it consteval. I'm going to have to skip a little bit. All right, so which functions do I make consteval by default? Those that are already Constexpr and the arguments that they have are guaranteed to be constant expressions, such as no parameters, or they're guaranteed to take compile time literals, like UDLs. Which functions do we choose to make consteval? Those where we want to force for compile time, like runtime efficiency, we want to force them to compile time, or functions where we want to force it to compile time for safety, such as our string view idea. Yeah, that's a good place to take a picture. Well, it is. That's a good recap. More specifically, make these things consteval by default, functions that take compile time literals, functions that are problematic at runtime, free functions that take no arguments, default constructors, they take no arguments. All right, what is left? How do we test consteval functions? And I've got like 8 minutes to do this. How do we debug consteval functions? Okay, if it compiles, we know that there's no undefined behavior, asterisk, dependent on implementation, and it is correct and passes the test, right? If this program compiles, I know it's correct. Sorry, all right. Okay, so if you're using catch 2, then you can use the static check thing, and it will do a static assert on it. In fact, I was just playing with these in one of my scripting engines. Testing Constexpr. Now, if this is a Constexpr function and I'm using catch 2, then I'm going to do something like this, and I'm going to compile my test code 2 times. I outline this in my C++ best practices book, and also in my C++ my CMake starter projects. I compile my test suite 2 times. Once without this catch config runtime, and once with it. And so if I compile it the first time, this thing on line 7 is a static assert. If it compiles, I know it's correct. The second time I compile it, it's not a static assert, and now I'm allowed to jump into the debugger here. That's great. But I already said there's a problem with consteval functions in that they, that's all the wording for that. Consteval functions don't exist. They don't exist. It's literally impossible to jump into the debugger with a consteval function. So you're not going to debug it. So if I've got some sort of complicated computation and it's not returning what I wanted it to, I can, execute this thing with an assert and I can get a runtime error, but that doesn't help me debug it. So I can't. No code omitted. We already said that. All right. So how do I check these intermediate values? Using a static assert here is simply not going to compile. Because static assert requires constant expressions. Are x and y constant expressions? No, we all know that now. Okay, if I put an assert in here, then I can get this thing to fail to compile if it doesn't meet my expectations. So I can do basically a guess and check. We all remember that from like algebra, right? I don't know. 42, let's plug that into X and see if it works. But that's basically the level of debugging we're talking about here. We don't get what X++ was, X plus Y was. So there's other ways of doing this. Like this is my combined version that happens to work with both GCC and Clang. This guess and check plus causing a floating point exception. So in this version, if I call it with GCC, then I get this like error, this number divided by 0. Oh, that's what the intermediate value was, thanks. Meanwhile, if I switch it over to Clang, then I also get the intermediate value where I get it here. I get it in a different place. I get it in the call to get value. So that's, yeah, there's just, yeah, all right. No. Debugging is difficult to impossible. If we look at this stuff, oops, sorry. Yeah, we already, shoot, I've got 4 minutes, 3 minutes. This is GCC. This is a Constexpr function. And is this thing, all the things that we just talked about, is result computed at compile time? No. Okay. That's optimized. There's a reason why I did all those previous examples with Clang. Was result computed at compile time? GCC evaluates Constexpr functions if it can. This function is already impossible to debug with GCC in this case. That's GCC's decision. So Consteval isn't necessarily making things worse for us, but we have to do this. I say, on every one of these slides, I've said, like, what about fuzzing? Or like, what about fuzzing? Or what about fuzzing? And I have to, we have to do this. I've spent too much time thinking about this and working on it. And I've got, well, I'll give you a QR code or whatever you can look at later. I've been left with one unescapable question, and it's basically do we care? Do we care about how well tested our Consteval functions are? And this is a tricky question. I get a lot of pushback. Beyond the most basic of test, does it matter? All right? So, no. So Consteval functions, these things can't be sanitized. Generally speaking, when we talk about fuzzing, we talk about turning on our address sanitizer, our undefined behavior sanitizer, our thread sanitizer, and then we run the fuzzer, right? And we see what falls out. But we can't. There's no code. They can't be fuzzed. That's impossible. So there's 3 possible outcomes of executing a Consteval function. 1, I get the correct answer. 2, I get the incorrect answer. 3, the code doesn't compile. That's it. It's impossible for this code to leave undefined behavior behind in your program. So it's as just a philosophical question, spend the rest of the week and whatever, asking yourself, how much testing do we need to do of Consteval functions? All right. That's all. I did write something that attempts to fuzz Consteval functions, by the way, at compile time. It automatically at compile time generates a set of interesting parameters to pass to your Consteval function and then tries to evaluate them all. But the problem is, you're never going to debug it. It's just going to fail to compile. And you're not even going to know which inputs failed to compile. All right. So, keep your functions small and testable. That's a good thing no matter what, and it makes them more accessible to your LLM. Most UDLs, I know I'm out of time. Most UDLs should be consteval. Almost all parameterless functions should be consteval. Consider making your default constructors consteval. Anything you want to force to compile time for safety should be consteval. And anything you want to force to compile time for performance should be Constexpr, then wrapped in a consteval lambda. That's the better, more usable, reusable thing there. Be aware that there's a bug with consteval and static Constexpr and Clang, but I don't have time to get into it. It's a really serious bug. Test your normal range of inputs. Don't worry about other tests. I don't know. Anyhow, that's the end of my talk. Consteval, all the things. Be sure to contact me if you want training or whatever. And that's my YouTube channel, QR code. This thing, the Constexpr, understanding the Constexpr two-step, the talk that I already talked about from C++ on C, they're breaking it down right now. Go watch that talk, and otherwise, thank you for coming to my talk.